Yeah.
Like he reviewed like the Gen Chem concepts, like why alcohol is
But like
polar.
why is it like an OH group like polar is because like electronegativity difference. I don't know. He just like wanted to
Mm.
emphasize that for some reason.
Yeah, yeah, that's good. That's good. That's chill.
Yeah.
Did you guys start learning like any nomenclature,
Yeah, he
predictive
did like a little bit of nomenclature. He was
properties?
like, oh, this is like how you name it.
That's good. That's good.
Like a bunch of examples.
Uh-huh.
Yeah.
Did he go over any reactions like predictive product?
No Mac, no Mac.
Mech.
He like Professor Beal, he only emphasizes like name to structure, not structure to name.
Oh, name the structure, like not.
Yeah.
Oh, like not draw the structure from the name. I
No, you
see.
draw the structure from the yeah, draw the structure from the name.
Oh,
That's
draw the structure from the name. I
yeah.
see.
But not the other way around. Because like
Yeah.
he finds it like, oh, in the real world, you just use Google.
There you
Yeah, he's not like Leavens, where it's like, oh, you have
go.
to go back and forth.
Yeah, yeah. Levin's like she expects you to know both ways, like going from the structure to the name and the name to the structure. It's
Yeah.
crazy. What reactions have you learned so far about alcohols? Like, did you learn about the HX reaction, the H2SO4 reaction with heat? What mechanisms have you learned so far about it?
Oh, like from 128.
Yeah. Like did he go over any
Oh,
mechanisms or not yet?
yeah, yeah. We learned how to like add alcohols onto like an
Mhm.
alkene, but it's
Oh, adding alcohols onto alkenes, like with acid and water, like H2SO4 and water.
yeah, like protonating and stuff. And
Protonating, yeah,
like
yeah.
uh I'm trying to find my note card. My
Yeah.
Chem one.
Uh-huh.
Oh, it's right here. No, no, it's not. Oh, I left it somewhere.
Something like this, similar.
Uh, yeah. There's like alkene involved.
Alkene, yeah.
Yeah. This
Can
hydration, right?
Yeah, hydration.
Hydration.
Do you remember how we would start this type of problem? Like what the
Yeah,
first
the alkene is like
uh
the electron. No, wait. It's electron rich, so it should be the nucleophile
Yep.
that
Mm-hmm.
attacks the the H on the H2SO4, one of the H's. Yeah.
Mm-hmm.
And then the H will add on the left subside.
Mm-hmm. That's correct. Right, right.
Okay, this reaction. There will probably be a carbocation shift.
Yep. Mm-hmm. Because once we form the secondary carbocation here, we see that we could do a carbocation shift to convert or shift the carbocation
Yeah.
to the more stable position, the more substituted position. Nice. And we lose the stereochemistry there because it is now.
Becomes sp2.
Yep. Yep. SP2, flat and planar.
And then the water as the solvent comes in because it's more
Yep.
abundant.
Mm-hmm. Water as solvent comes in, attacks that. It's more abundant, and also, if you look at the conjugate base of the H2SO4 that we deprotonated, we have a
It's
negative
not
charge.
nucleophilic, right?
Yeah, it's not nucleophilic
Yeah.
because this negative charge
Resonates.
here, what can it do that makes it more stable, you could say?
Resonates. Resonates.
Resonates, right? Because it could do resonance, it makes it more stable. And if it's more stable, it is less reactive, less nucleophilic.
Yeah.
Right. But water here, the oxygen has nowhere to resonate. So that's why it's less stable, making it more reactive, more nucleophilic, which is why it is going to attack that carbocation to give us
Like
this intermediate.
yeah.
Right.
Wait, what do you call the water ion? Is just
Oh, oxonium ion.
plutonium. Okay.
Yep. This OH2 plus on an alkyl group is an oxonium ion. Right.
Yeah.
OH2 plus or H2O plus on the alkyl chain. Right.
Yeah. And then the HSO4 minus comes in to take the H
Mm-hmm.
to
Yep.
balance the charge out.
Yep. Takes the H, takes the charge out of the oxygen, and that also regenerates our acid catalyst,
Yeah,
the
acid. Yeah.
H2SO4, right? And the reason why I did not put wedge or dasher is because when the like
Isn't it racemic?
yeah, it's racemic. When
Yeah.
the water attacks that carbocation, it could either attack on the top side or the bottom side because it's flat and planar. So that's why it would be
Yeah.
racemic in this case. But be careful here; it will not always be racemic depending on the molecule because if this is not a chiral center right here, then we cannot say racemic because
Yeah. Yeah.
racemic is a one-to-one mixture of enantiomers. If let's say like we had something like this, then that would not be racemic
Yeah.
because this is not a chiral center anymore. Yeah.
Yeah.
Okay.
So you get it wrong if you drew like a wedge and dash.
If you drew wedge and dash,
Yeah, just for the.
that is technically correct, but I would put like
Oh yeah.
plus enantiomer,
Oh, I see.
or the way that Helix does it, he does the symbol to show that it
Oh, I didn't know
include
that.
the other enantiomer as well, like the dextrorotary, levorotary,
I see. I see.
right? Kathy, this is what you are going to be learning at the beginning of 118B, the hydration of alkenes. Yeah, but you learned about this in 128A, right? Right.
Yeah.
Yeah.
Yeah. I think alkene stuff is not that bad.
Mm-hmm. The bad reactions, in my opinion, are like the oxymercuration, demercuration, and
Oh yeah,
hydrogen.
yeah, yeah. You have to draw like the mech. It's like kind of long.
Yeah. The mech for that part is annoying, but like knowing the product behind it is not that bad. But the mech behind it
Yeah.
is long.
Yeah. Um,
Mhm. Um, that's a good thing to teach Kathy because she's gonna learn about alkenes right now. And let's see
yeah.
here. Let me pull up my notes to see how Helix teaches this.
I think Felix today he just taught about the syllabus and then like nomenclature.
Yeah. He starts off with
That's it.
nomenclature. Right.
Yeah.
Okay. Kathy, do you
Um,
want to start off with nomenclature or do you want to skip straight into the reactions? Reactions? Okay. There's also properties like melting point, boiling point. Okay. Here's the first reaction that he taught about alkenes, which is hydrogenation of alkenes. So when you have some sort of alkene like this, just some random alkene, and you react it with these reagents, H2PDC, what do you predict is going to happen? No idea. So we have two hydrogens in the reagent here. That means that we are going to add two hydrogens in the alkene here, right? You can think of it as converting an alkene into an alkane, like a double bond to a single bond, because when we do that, we are adding two hydrogens, one for each carbon of the alkene, right? This carbon here, before it only had one hydrogen, but now it has two hydrogens, right? This carbon here, before it used to have two hydrogens, but now it has three hydrogens, right? So these two hydrogens here that I circled in blue are the new hydrogens that came from the H2PDC, right? So you could think of this as reducing an alkene into an alkane, right? Just converting an alkene into an alkane, a single bond, a double bond into a single bond, but that adds two hydrogens. And when this happens, this will release energy, right? And the energy is going to be called heat of hydrogenation. And you can see that as a symbol right here, which is heat of hydrogenation. Right? Okay. And heat of hydrogenation is going to determine the stability of an alkene stability, right? This is a measure of alkene stability. And think of alkene stability as similar to carbocation stability. Do you remember the ranking of carbocation stability from 118A? Yeah, so what would be the tertiary carbocation is more stable than secondary carbocation, which is more stable than primary carbocation. Another way you can say that is that the more substituted carbocation is more stable, right? It's the same for alkenes. The more substituted the alkene is, the more stable it's going to be. So this is going to be mono-substituted. Oh no, this is an unsubstituted alkene because there's no substitutions around the alkene, right? Even though there are hydrogens in this alkene, we don't not count that as a substitution. A substitution is going to be like an R group, an alkyl group. So this alkene here that I just drew out is unsubstituted. There's no R groups around it. This alkene right here is mono-substituted because we have one R group, and we have three types of di-substituted alkenes, right? We have the geminal. Oh no, that's cis. Geminal alkene, cis alkene, and trans alkene, right? So these three alkenes right here are di-substituted alkenes. This alkene here is unsubstituted. This alkene right here is mono-substituted. And then this alkene right here is tri-substituted because there's three R groups around that alkene. And then the most stable alkene here is going to be this tetra-substituted alkene, where there are four R groups or alkyl groups around the alkene, making that the most stable alkene. Right. So the more substituted the alkene is, the more stable it's going to be. But this geminal and cis alkene will have similar stability, right? But the trans alkene here is going to be more stable than both the geminal and cis alkene. And can you think of a reason why the trans alkene is the more stable di-substituted alkene compared to the geminal and cis alkene? Like what is one factor you can think of in 118A that makes this trans alkene more stable than the geminal or cis alkene? Yeah, the R groups are farther away from each other, which is going to have less. What? Do you remember the specific name, specific factor? Steric hindrance. Yes, steric hindrance. Steric hindrance. These R groups here avoid steric hindrance, whereas the R groups in the cis and geminal alkenes have more steric hindrance because they are close to each other. They are bumping into each other, increasing steric hindrance, which makes it less stable. Right. So tetra, it looks like there's a lot of steric hindrance going on here, but it is more stable because it has more substitution, more hyperconjugation, you could say, around the alkene. So that will overpower the steric hindrance effect, right? The R group substitution will overpower the steric hindrance effect. But all of these alkenes right here, the geminal, cis, and trans, they're all di-substituted alkene because there's two substituents around it. So the difference would not be based on the substitution because they're all equally substituted. It would be based on steric hindrance now. Right. So the arrows I give here is going to be based on stability, right? Stability of the alkene. But what if I reverse the arrows and put it in red? What factor would you say increases from right to left in red? Right, what's the inverse of stability? What factor can you think of? Right? If a molecule is more stable, what does it have less of? Yeah, reactivity. You can think of it like that. There's another thing, which is going to be energy, right? The more stable something is, the less energy they have, and the less energy they have, the less reactive they are. So they are kind of similar like that, right? The more reactive something is, the less reactive it is, or the less energy it has, right? So energy and stability are inversely related. You can also think of it as reactivity. Yeah, more stable equals less energy, which you could also think of it as less reactive, right? Because if you have less, if the molecule has less energy, it's going to be less reactive, right? So based on this, we can think of energy as a form, like a form of energy is going to be heat of hydrogenation, right? So if I give you this type of problem right here and tell you to rank the following alkenes in order of increasing heat of hydrogenation, where one is going to have the highest heat of hydrogenation and 5 is going to have the lowest heat of hydrogenation, how would you go about this problem? Wait, what's your thought process here? Highest heat of hydrogenation is going to be at the most left side. Yes, that's right. Lowest heat of hydrogenation is going to be the most right. That's right, because that's the most stable, having the lowest heat of hydrogenation. So that's 5. Second highest is 3rd. So the second highest is going to be the 3rd one because that is the second most unstable alkene, making it have the second highest heat of hydrogenation. That's correct. Four is 4th. Yep, 4 is going to be 4th, the trans alkene. And that would make the second one the 3rd one. Yep, you got it. Right. Because this one right here is going to be the least stable alkene, the unsubstituted alkene, and because it is the least stable alkene, it will have the most energy, aka the highest heat of hydrogenation. If you see a question asking to rank the following in order of heat of hydrogenation, think of that as energy. When you react these alkenes with H2PDC, they will release energy or heat, which is called heat of hydrogenation. This alkene here on the right is the most stable, having the least energy, which will release the least amount of heat of hydrogenation, and everything else is in between, based on this ranking list right here. Nice. Uh-huh. Ooh, Wiley, I want to teach you this alcohol reaction here with nucleophilic acids,
Okay.
which is
Is it
known
something I've
as
learned? Uh,
HX,
HX.
right? Where X could be chlorine or bromine, like HBr or HCl, like hydrochloric acid
Yeah.
or hydrobromic acid. Um, I think you can solve the problem already when I show you the problem. Like just think about it intuitively, what would happen in the mechanism, and I think you can solve it. Let me make a problem for you here. Let's see.
Have I learned it before? I don't know.
I'm not sure. Let me just show it to you, and then let's
Okay,
see
okay.
if it looks familiar. And if it does, you might have learned it before, but if not, then I think you can solve it anyway. Okay.
Wait. Oh, I don't think I've learned this with the
Mm.
alcohol reactions. Yeah.
Hmm. Yeah, yeah. So we have a strong acid, HX, a nucleophilic acid. So when we have any kind of strong acid, we look for the most basic atom, right,
Most basic.
in the molecule we have in the reactant, right? So which atom do you think would get protonated by the HBr?
Oh, it has to be the alcohol, right?
Yep, the alcohol, the oxygen.
Yeah.
The oxygen here of the alcohol is going to grab that hydrogen of the HBr and then kick out the Br as the conjugate base, right? When that happens, what is the ion name that we are going to form here?
Octonium. So
Ozonium ion, yes. And we just converted a bad leaving group,
they're
alcohol,
good leaving.
into a good leaving group,
Okay.
oxonium ion. Now we can think of this as an SN1 like mechanism. Now, what would be the next step once we have a good leaving group for SN1?
A carbocation intermediate forms.
Right? We kick out the leaving group
Use all. Yeah.
to form that carbocation intermediate.
Yeah.
Yeah. Then once we have this carbocation intermediate, what would be the next step?
Uh, what is shift?
Yeah.
Okay.
hmm It would do a hydride shift to form the more stable carbocation. And then from here, once we have the more stable carbocation, Br minus can just come in, attack that carbocation to give us our final product, like that, right? So think of it like SN1 type mechanism, but we first have to convert the bad leaving group into the good leaving group, oxonium ion, by protonating the alcohol with the strong acid we have, right? And the reason why this is called a nucleophilic acid is because
You're
when we,
adding the nucleus, the Br or the halogen. Yeah.
yes, the halogen here uh, acts as a nucleophile after the HBr gets deprotonated, right? So a non-nucleophilic acid is going to be like H2SO4 or H3PO4,
Yeah.
right? Because when you think about the conjugate base, why is the conjugate base not nucleophilic of like
It
H2SO4?
has lots of resonance, so it's like
Yeah,
really stable. It won't add.
that's correct. It has lots of resonance, making it more stable, less reactive. It won't be able to attack. Let me give you one alcohol problem with a nucleophilic acid and heat, and let's go through that. Let's see. Let's do this, this, OH, and let's react this alcohol with just H2SO4, nothing else, and high heat, high temperature. Right.
Oh, there's high. Uh,
Uh-huh.
you just draw like the delta just to represent heat? Like, do you need like a specific temperature or is it just heat?
For leave-ins, she will specify what temperature is high, what temperature is low.
Yeah, yeah, that's what's confused on.
For bio and helix, I don't think they
Okay.
specify the temperature. If you see that delta symbol, then assume high
Yeah,
heat.
yeah. Okay.
So let's work through this problem. Let me know when you have an idea of what the first step would be like.
Wait, would it just move the alcohol around on the
So
wait, H2. No.
right, we have a strong acid, and whenever we have a strong acid, we first look for the most basic atom that can get protonated by that strong acid, which is this alcohol oxygen. So this is going to be a very similar first step. We are going to make the oxonium ion, which is a good leaving group.
Uh-huh.
And then once we have the oxonium ion good leaving group, what do you think is going to happen in the next step?
It leaves.
Yep,
Oh.
carbocation rearrangement, it leaves. And then once we have that carbocation right there, what reaction would be major or favored when we have heat? SN1 or E1?
Wow. Okay, I'm not gonna lie. I didn't 128A did it cover the heat part. We just learned like, oh, if it's SN1 and E1 if and it's just like different ratios based on how much
Uh,
nuclear the other is. We didn't talk about anything about heat.
oh, I see, I see. When you
But
see,
I can probably learn it.
yeah, heat,
Yeah.
that's gonna favor the E1 reaction over SN1 reaction because usually SN1 and E1 they go together, right? Like
Yeah,
right
yeah.
after the good living group leaves, and you have the carbocation, and then you see if you could do any shifts like a hydride shift or metal shift. That's when you go for SN1 or E1, and usually SN1 is major over E1, right? But they will always go in combination with each other. Like they always happen at the same time. But usually SN1 is major over E1 unless you have heat. If you have heat in the reaction, that would favor the E1 reaction, right?
Yeah, okay.
Uh-huh.
Is it because E1 makes more products and that's why it's like favorable because if you heat up something, you make like
Yeah, it would have to do something with thermodynamics and entropy.
yeah,
Uh,
yeah.
with the Gibbs free energy equation,
Yeah.
that heat symbol, that when you increase heat, that would like favor the
The,
more
the
product,
more, yeah, yeah, more okay. That
right,
makes
right. Uh-huh. So now, which beta hydrogen would you want to grab to form the more stable alkene?
the one on the left because if you
Yep.
do the one on the right, you get a primary and primary
Mhm,
carbocations are not favorable at all.
mhm. Oh, when we grab the one on the right, we form a mono substituted alkene. The carbocation is no longer there, right? The carbocation
Yeah,
is
yeah.
going to be here, but it's gonna be a
Less
mono substituted
substituted. Yeah.
alkene, right?
Yeah.
But it would be the one on the left, making that alkene right here. But for leavens, right, she would give these two as two possible products, right? Both the trans and cis alkene, where the trans would be major over the cis. But do you
Yeah,
know
yeah.
how we would be able to get that cis alkene from this intermediate?
Um,
Think about this single bond and what it could do.
oh, it could rotate.
Yeah.
Yeah.
When it rotates, we can get this same structure, right? But this is now just up there, and then when we deprotonate it from this angle, then that would lead us to the cis alkene. But this would be considered minor. This would be considered major. But for Levin's tests, you would have to include both products. But for Beal, I wouldn't worry about that. I think he would. Oh, well, I don't know yet, but we'll see. But I don't think
Yeah,
he's as
yeah.
specific as Levin's like this.
Yeah, yeah.
Right. And I think from the last quarter's final review session, you learned about these alcohol reactions right here, where when we have this alcohol, there are some reagents with
Oh
weird.
yeah, yeah, yeah. Oh my God. Oh, I
Yes.
remember this. Wait. T- Wait, I don't know. I didn't learn this one. I don't. No, I didn't learn it.
Uh-huh. Right. So
There's one similar one. It was just adding an alcohol, like a beta or like an alpha one. But oh no, it was for the alkyne. Sorry, I get confused.
alkyne. Yeah.
The three.
That's dang, you learned about alkynes, right? I forgot about that. That's later on
Yeah,
in B.
yeah,
That's
yeah,
after alkenes.
SN2 like reaction.
Mhm.
Mm.
So what this would do is convert the alcohol, and let me add this here. So I emphasize that there's no carbocation shifts that are going to happen here. It's just going to convert the alcohol where it is at to the
Oh,
halogen
okay, yeah, yeah.
that it has and invert stereochemistry. Mhm.
Is it only for alcohols? It will only attack the OH.
Uh,
Oh no, yeah.
you will see these reagents again later on for
Hmm.
like carboxylic acids as well. But
Oh
um,
yeah, yeah, yeah.
that's for later on. That's for later on.
No, I have to learn carboxylic acids for 120B.
Oh, 128B carboxylic acids. Is that the
Yeah.
first unit or is that the like
It's
the
near the end, I think.
near the end?
I
Okay,
learned
okay.
the carboxylic acids and their derivatives
Yes, yes.
because I'm
Like
a
the
syllabus.
esters, amides,
Yeah, yeah, yeah.
hydrides, everything. Mhm. Okay. Okay. So this would just invert and convert the alcohol into the halogen based on what reagent we use, like that. Right.
Oh, it's just for each respective halogen. Okay.
Yep. Each respective halogen. If you use
Yeah.
SOCO2 that has chlorine in it, then you just substitute the alcohol with the chlorine. If you used PBr3, you would substitute the alcohol with the bromine. If you used PI5, then you would substitute the alcohol with the iodine. But you would always invert stereochemistry. Like
Yeah,
in
yeah.
this case, we had the wedge, and that converted to dash. If that was started as a dash, then the product would have a
Yeah.
wedge.
Is there one for fluorine or is it just too reactive?
Uh, I think it's too reactive.
Oh yeah,
I
yeah.
haven't seen one for
That's what I thought.
fluorine. Let's
Okay.
see. There's more alcohol reactions.
Oh yeah, for the nucleophilic acid, why can't you use HI? It has a higher pKa, right?
Oh,
Like
you
it's
can. I think. Let's see. HI. Can you use HI? Let's see.
for yeah, this one, the HX. Can you use
Chlorine, bromine.
or does it just is the reaction just too slow for this?
I think you could actually do HI as well. Don't quote me on that, but I haven't
Okay.
seen a lot of HI reactions with this. I've mostly seen CL and BR, but if it doesn't work, then it would have to be something about like it's too endothermic. It would be too slow.
Yeah, you need yeah, it's like slow. Yeah, okay, that's right.
Yeah, yeah, yeah. Nice thinking.
Uh,
Hmm. See.
Are those like most of the are there like wait, how many like reactions for alcohols are there for
There's one where let's see here. Well, you could react an alcohol and convert it into an ether with Williamson ether synthesis.
oh ethers, yeah.
Ethers. And then after this reaction, I'll check my alcohol reactions and see if we're missing anything. Williamson ether synthesis. It's a two-step synthesis where the first step is an acid-base reaction. The second step is an SN2 reaction. Right. So if we have this alcohol here, we're gonna have two step-by-step
Oh, it's like a one
reactions.
two type of
Yeah,
thing.
1, 2 kind of thing. The
Oh,
first step is gonna be some kind of strong base,
okay.
and the second step is gonna be some kind of alkyl halide or haloalkane, like let's say this, for example. Right. And I'm gonna have you explain to me the mechanism and predict the product after each reaction here.
Okay. Oh, is this it for the like what you
Uh-huh.
wrote?
Yeah, this is
Okay.
it. This is the reactant. These are the reagents. Let's focus on the first reagent and this alcohol. Whenever you see sodium, what charge is that associated with?
Plus one.
Yep, plus charge. That means that whatever is
Hydride.
attached to it, yeah, is have minus charge. Yep, we have a hydride ion, which is one of the strongest bases we have. Right, the H minus is very unstable because hydrogen is very small. It can't handle that negative charge very well, and it's not electronegative, so it's very
Yeah.
unstable, very reactive. Right, so that's going to be our very strong base. Yeah.
Oh, so it's just gonna literally just like steal. the electrons from the OH bond, right?
Yep, it's going to grab or deprotonate the alcohol, the OH. It's going to take that hydrogen of the OH, and the electrons from this bond between the O and H is going to go
Oh,
onto that oxygen
okay.
right there to give
Right.
that oxygen a formal charge of,
Should be minus
yeah, -1. And then this is just a side product,
H2. Yeah.
H2 gas. Yeah. Now that's the end of the first reaction. Let's bring in our second reaction now and see what that would do.
I'm thinking like O minus like nucleophile. There's a polar bond involved, right?
Mm-hmm.
So it's gonna attack the carbon bromine bond
Yep, that's
and
right.
break the Br off.
Mm-hmm. Yep. Attack that, kick out the Br, SN2. Our nucleophile here is this oxygen with a negative charge.
Uh-huh.
Our electrophile here is this partial positive carbon. And our good leaving group here is this bromine.
Bromine, yeah. And then you just add the carbons onto the oxygen.
Mm-hmm. That's correct. Add the carbons onto the oxygen, which is a 1, 2, 3 carbon
The
chain.
carbon.
One,
One,
two,
two,
three.
three.
Yeah. And then you could include this, but this is not organic. So if this was predicted product, this is not required in the product.
Oh,
But if this was mechanism, then this might be required 4 points for mechanism.
okay.
And this right here, what functional group would that be?
Should be ether, right?
Yep, ether, which is why this is Williamson ether
William ether
synthesis,
synthesis. Okay.
converting alcohol into an ether. That's right. Let me check my notes if there are any other alcohol reactions real quick. Um, there's formation of alcohols, which we can go over.
Formation? Oh, it's not like adding.
Yeah, it's not
Okay.
like reacting with alcohols. It's making alcohols from haloalkanes, you could say. So if I started with this haloalkane right here, and I wanted to substitute that bromine with an OH alcohol, what reagent could I use?
Oh, is this like the SN1, SN2, U1, E2 type thing?
Yeah, SN1,
I don't
E1,
remember.
SN2,
Let me
E2.
pull up the table.
Yeah, yeah,
I have my note card.
yeah.
Oh,
Let's see.
should be SN. Oh wait, no. Yeah, just SN2, right? SN.
Yep, SN2.
Hmm.
SN2, we're substituting this bromine with this OH, and because uh, this substrate here is primary substrate, primary unhindered. So
Mhm.
what would be the specific nucleophile required to carry this reaction out?
Unhindered. Use a weakly basic one, so you could use like cyanide ion or HCN. I don't know.
So
Or
if
like any one of
we
the H2S.
yeah, that's the common SN2 reagents that we use, like the weakly basic strong nucleophile reagents for
Oh, but
SN2.
we want to add the OHS specifically, right?
Yes, yes, we want to
Oh,
add the OH
okay.
specifically. Mhm.
Oh, this is
So it does not have to always be a weak base. It could be a strong base like
oh yeah,
OH.
strong. Yeah,
Yeah.
strong 100.
Uh-huh.
Oh, just an OH minus,
Yep,
like
OH
NaOH.
minus. And that could be in the form of NaOH or KOH. Same thing, right?
Yeah. Oh,
In
okay.
in water solvent. But this is only possible for primary substrates, right? Because this is a primary substrate, we are able to convert this halogen into that alcohol right there.
Uh-huh.
If, for example, we had a secondary substrate like this, and we wanted to um, convert that halogen into this alcohol,
We would
we
have to use
cannot use NaOH
yeah.
water because That would no longer be SN2. What reaction
You
would that
get E2 Zaitsev.
E2? Right, right.
Yeah.
That would give you this product instead, which is not what we want. We do not want the alkene. We want this alcohol.
Yeah.
So to do this, this is a two-step synthesis or reaction, step-by-step reaction that Levens loves to do sometimes, converting a secondary halocane into an alcohol. Do you remember what would that be? It's okay if you forgot.
It's a two-step process of
Uh-huh. So the first step would convert the halogen into some sort of different functional group. It would be SN2 though, like with a weak base strong nucleophile. And then once we have that functional group, we do a 118C reaction that we don't need to know the mechanism for, but for Levens, she wanted you to do the reaction for. I don't know if you remember that last step, which was a 118C reaction. But
isn't it the thing that Farrah had taught and then he just like he just put it but like he wouldn't teach it.
yeah, it
Like
was it
is it
was
ester hydrolysis or something? Or is that
yeah,
like
ester
oh my
hydrolysis.
God.
Yeah, you remember. That's good.
Yeah, I remember. It was like I just remember because it's like a joke. It was like a meme. It was like
Yeah.
he like teaches you like I don't know why he includes it, but he didn't teach the Mac. It's like I think it's like stupid, but
Yeah. The mech is one of his thing. That's why. But he just
yeah,
show it to you, and they expect you to know the reaction and what it does.
yeah. Oh, that's weird.
Mhm.
Um,
To do that, we are gonna use this like acetate.
oh,
We're
that's
going to say
okay.
carboxylate. We're just
Yeah.
gonna do SN2 because this is a weak base, strong nucleophile that is
We,
going to attack that carbon, take out the leaving group, invert stereochemistry, and give us this ester here, SN2.
yeah. Okay.
And then this is a 118C reaction here. To do ester hydrolysis, like you said, um, there's different reagents you could use. If the most common one that I've seen is NaOH, water as the first step, and then second step acid workup. Or you could just go use
Uh,
strong acid and water and heat, right? But you'll learn more about that at the end of the quarter when you learn about carboxylic acids and their derivatives, right? Ester is one of the derivatives. You learn more. You learn about this mechanism this quarter for 128B.
yeah.
But this last reaction here is ester hydrolysis, which basically cleaves that bond between the carbonyl carbon and oxygen to get that alcohol, and then this
Oh,
thing
okay. I see.
here becomes the carboxylic acid parent functional group. But they didn't really include that in the product, but that will get formed, and this will be very important because that is the parent functional group for the whole
Oh,
derivative family.
I see. I see.
Yeah. Mm-hmm. Okay.
What about like a tertiary, or is it?
A tertiary one, let's say we have something like this, and I react it with water. What would this do?
Tertiary would be it's just SN1E1.
Yep,
Like,
SN1E1. Um, but the major product here would be SN1 because we do not have heat or the delta symbol. So when we carry on with the SN1E1 mechanism, kick out the leaving group from the carbocation, there's no shifts here because it's already at its most stable.
yeah.
Then we just like do the whole thing, and that's how we can get another alcohol. Right? That's another way that we could form alcohols. SN1.
Ooh. Oh, okay, okay.
Yeah, we did this earlier today at the beginning of the session, like when we did SN1 with water.
Oh, yeah.
But we had H2SO4 as well. In this case, we just have water, so we can't use HSO4 minus as a base to deprotonate this oxonium ion. We just have to use another equivalent of water because we have excess
Oh,
amount.
yeah.
Right? That's another way where we could form alcohol. Oh yeah, how could we forget the redox reactions? Remember the PCC, Jones, lithium aluminum hydride, sodium borohydride of
Oh, yeah, yeah, yeah. All
alcohols?
that.
Yeah.
Yeah.
That thing too. And then
No, I didn't learn any of that, but.
Uh-huh.
Um,
Oh, you didn't learn
but
any
yeah,
of that. Whoa, for 128.
yeah,
Oh, I think that's this quarter, huh, for you, like the alcohol reaction.
probably yeah, yeah.
Yeah,
It's like the end of like 118A, like all in the beginning of 128B.
yeah. I
Yeah.
see, I see. 128. Okay. Yeah, yeah. And then the non-nucleophilic acid, it will depend on what temperature you're in. If you're in low temperature or high temperature, you would do SN2, A2, or SN1, E1.
Mhm.
But that's more of a leavens thing. Like that's when it gets like very nitpicky and the line thing. But I don't want to teach you that yet, just in case BO like doesn't go through to that, and I don't want to teach you
Yeah,
leavens
yeah, yeah.
zero when BO would not teach you that. But it's still good to know like different perspectives of different professors. Just
Yeah.
to see.
Leavens just test you on everything.
Yeah.
I think Beal is more chill with what he.
Yeah, he seems more relaxed, huh? Like
Yeah.
you,
I don't know.
you
In the
plan on
beginning of
going to
class,
his.
he's like a lot of 128 students like join my lab or whatever. I don't
Oh,
know.
well,
Or like all the people who join are like they took the 128 series.
oh my God.
Yeah.
Yeah. Do you plan on going to his office hours like you did? Uh,
I'm not sure. I don't even know
Philippines?
if I have time. I don't think I have time.
Yeah,
But there
that's
are TA office hours. So,
that's good. Do you recall anything about Grignard reagents, organic metallic reagents?
no, we didn't learn Grignards.
Oh, okay, okay, okay. But you heard of it though.
Yeah, I've heard of it from
Yeah,
the review session.
right, right, right. Okay, yeah. So tomorrow we could definitely go over redox reactions of alcohols and organometallic or Grignard reagents of alcohols.
Yeah.
And you have a head start on that. That's good.
Is that all for alcohols? It's just
That redox organometallic nucleophilic acid.
uh-huh.
We went over that already. The non-nucleic acid, we went over that, but Leibniz makes it a little bit like weird with the temperature, like high temperature, low temperature. So we'll see if BO does that too. Let me check my
Yeah.
other notes.
Yeah. Oh yeah.
Nucleophilic
I have to also learn like HNMR. It finally.
HNMR. Oh, this time for
I wanna-
128. Uh,
Yeah,
yeah, yeah. Dang.
finally.
Yes, yes, finally. Well, I remember, like, did you learn IR when you
No,
did?
we didn't learn any spec. It's just all mech.
Oh my gosh. Will you learn IR first before HNMR though for this quarter?
Well,
Or
the first time I learned IR was from you during that group.
yeah,
Yeah.
I remember. Yeah.
It's just like, oh, you just memorize it, or just look at the graph and then
Yeah, yeah, yeah. Wasn't
this
that
is
the
the
first
lava
session you
cone.
joined? Like my office hours, and then you just like hopped on the
Yeah, I don't
IR.
know how yeah. I was like,
Oh my
just
god.
like literally just look at it and then recognize the pattern and then that's
Yeah.
the functional group.
Right, right. Mhm.
Yeah.
Yeah, so that's basically it with the alcohols. And after alcohols, we learned about ethers, like the ether reactions. Uh,
Uh, do I even learn ethers after? Oh yeah, ether, alcoholic ethers, and then sulfides, and then epoxides, aldehydes, ketones, carboxyl. Yeah, okay.
oh wow, dang. Wait, so you're not dang, so you skipped the whole benzene
Oh, we learned. Oh, I think benzene might be one. I'm not sure.
yeah, dang. Is there what 128C or is this just 128A and B?
For what?
For the series, like with the 128
Oh
series.
yeah, it's to C
Oh,
128.
it's 2C, I see, I see.
I
So
think
they might
Leavens
put
is
some
teaching it spring quarter.
uh
Uh,
oh wait, who's teaching it spring quarter?
Leavens.
Oh, Levens. Okay, okay. I thought I heard the series for a second. I was
No,
like,
no, no,
did
no.
she make a comeback?
Yeah, I might have her again.
Yes.
Like I know what to expect. Like
Hmm.
how she structured her class. Like it's all
Yeah.
part of the game, you know?
Right, right. And the time is like
Yeah,
the Achilles heel.
yeah. I feel bad for all the 118A kids. I went to her lecture like I had nothing else to do. I had like a
Mm-hmm.
break. Yeah.
Oh, today?
Yeah. She was
Dang.
like lecturing Kleiber.
Did she see you? Did she recognize you?
I mean I just asked her like no because I originally I also wanted to go because I needed to ask her about like appointing like or like make booking an appointment with her to see my final 128A.
Oh, to review your
Yeah,
work
what
and
I got wrong. I got
what you
like
got wrong.
80% on it, like raw and like 86 with curve.
Yeah, dang, that's dedicated. That's dedicated.
Yeah.
Learn for you
Like
must
I don't know why her exam had like so many points.
It's all the vocab and her partial credit with the mechanisms and like the very
Yeah, I
small
don't know what I did wrong. I didn't.
nomenclature as well. Oh my gosh.
Yeah, to be fair, I kind of crammed that exam. I shouldn't have done that. I
Really?
thought she like curved the entire class along with the final, but she only curved the final, so
Oh my god.
that was
Yeah.
me.
How big was the curve for your
It was
course?
like 6%.
6%
I
for the
think
final.
the average was like a 72.
Oh yeah,
If you
yeah.
curve it like 6%, you get like a C plus basically.
Yeah.
Like
Hmm.
could be a 78. So
Yeah.
she just curved everyone up by 6%. And then that was just
For the final, right? Not the overall
yeah for
grade.
the final.
For the
And that was
final.
it. She just like that's your raw score. I'm like, oh man. Yeah.
Hey, that's good. That's good.
I like I know like how to like prepare for the quizzes now. Like I
Hmm.
don't think I was trying that hard for like after lecture. I didn't really review the notes. I thought it
Hmm.
was like, oh, I can like kind of cram it or whatever. Like I did a little bit of practice.
Yeah.
I didn't do all the yeah, I didn't do all the like as workbook problems or like textbook. I should have
Yeah,
done
yeah.
it.
That's definitely important. Like the like a lot of
Yeah, it's
practice.
really just practice.
It is. It is.
Yeah.
Dang. Okay. Well, thanks for coming tonight, Wiley. I will see
Yeah, no
you
problem.
tomorrow.
I might come tomorrow.
Hmm.
Yeah, I'll
Yeah,
definitely come tomorrow.
we'll see. Like whenever you do come, we could go over like the rest of alcohols, like redox, organic metallics, and
Yeah, yeah,
if you
yeah.
teaches it, like the temperature differences.
Okay, okay. Yeah.
Yeah.
All right.
Yeah. Good night.
Thank you. Goodbye.
Bye.